Okay, so we're I apologize first of all that I never got around to uploading a video last week for this class. Turns out I'm a little rusty on Laplace transforms, so this is just my way of trying to get back into this. Now, what I'm going to introduce today is it's a little different from Laplace transforms in that we have this big issue. If you remember, at one point we had a system that looked like this. This is a very simple model of a suspension system where you have a massless axle. This represented the tire. This was a spring that represented the tire, and then you had a spring and damper that connected the axle to the body of the vehicle. Now, when we had this system, the overall equation that we had for the force in this spring was the force spring 2 was equal to K2 times x2 minus x1. And that, no, that's not quite the equation. This was x2 minus x1 minus x naught, which was the original length of the spring. So when we had this equation, and this is the force in the spring, we were trying to figure out what that force in that spring was. The issue is it relies on both the displacement of those two members in order to really figure out what this is. And similarly, the force in the damper was equal to C times x dot 2 minus x dot 1, which relies on the velocity of both members. So if we're looking at, we're trying to solve for this mass up here, and we're trying to solve for what that distance is, we had a substantial integrated problem where now it's x2, x1 are both in the problem, and how do we solve that? Well, we end up getting two equations, and the equations have an x1 in it, has an x2 in it. They're really difficult to separate. So what we're gonna discuss right now is I'm gonna give you a simple problem, and we're gonna talk through how to handle it. And this is going to introduce the idea that we're really talking about today, which is systems of equations. Okay, so when it comes to systems of equations, oftentimes you will have multiple input and output variables where the output variables depend on each other. The performance of x2 depends on the performance of x1. x1 is itself an output variable here. So what do you do when you have these types of things? Well, you have to develop a system. Now, this class is called Systems and Controls. The reason why they're lumped together is because if you're trying to control system output, or trying to control an output, and you have a system involved there, which most everything is a system, you're going to have to understand how the system as a whole behaves. Okay, and as we talked about earlier this semester, system behavior itself, we can look at only one aspect, but when you have multiple outputs that are all intercorrelated, it becomes very challenging. Such as if the temperature changes, then the power output changes for a vehicle. And that does cause some serious issues, and it does make control systems even more complex. Control systems themselves are continuing to be one of the greatest areas of advancement in technology and engineering right now. It's for this reason. The math behind it is ridiculous. The science behind it can be pretty understandable, but it really takes a bright mind and a whole lot of commitment to make these control systems operate efficiently, effectively, and without error. So we're going to talk about what to do with the system. And I'm going to go ahead and take a very, very simple system where here we have a spring and we have a damper, and that's connected to mass 1. And then we have another spring, and we have another damper, and that's connected to mass 2. And I'm going to go ahead and exert force as a function of time on that bottom mass. And it's hanging from some kind of ceiling. Awesome. Okay. So as we look at this, we're going to do our sum of the forces in the y direction for mass 1. And that's equal to, first of all, you've got your, if we signify that this is positive direction of y, then just having this object, you have your mass 1, say you've got force in your spring, force in your spring 1, force in your damper 1, you've got force in your spring 2, force in your damper 2, and then you've got your inertial force m1 x1 double dot. We'll go ahead and state that this distance, this is 0, this distance is x1, and this distance is x2. Okay. All right. Now we know that this is equal to fs1 plus fd1 plus your inertial force m1 x double dot 1 minus fs2 minus fd2, which that's pretty ugly right off the bat. Great, and this is equal to 0 because we included the inertial force into this. So, sweet. And then we've got, for our second object, here, we've got our forcing function, which is f of t. You've got fs2, you've got fd2. Now, both of these are pointed opposite of each other. That's because we're assuming that this is in tension. We're assuming that this is providing a tension load. As long as these have the same sign convention, we should get the same answer here. Okay, so here are some of the forces. The y direction on 2 is equal to fs2 plus fd2 minus f of t. And plus our inertial force, which is m2 x double dot 2. And that's equal to 0 again. So we have this system that we're looking at. This is our constitutive equations. Okay, this is the physical relationship between our variables that has to exist in order for physics to be right. Okay, so this is ultimately how we develop our equations. And if you look at it, we know that this system is moving linearly in the x direction, which if you look at how our pairings go in this class, the energy equation for a linear motion system is F times x. So really, you're going to be looking for a function that has both F and x in it, because as the energy equation, F times x, that's ultimately going to dictate what the power transfer through the system is. And all this is just considering power transfer through a system. That's what most analysis is studying power. Particularly in this case. We want to know how energy flows through the system. So that's why we're studying forces. That's why we're studying displacements. We're going to put all of these forces in terms of displacements because that relationship exists because of the energies that are created by those forces, etc., etc. Okay, so here's our two constitutive equations. They're horribly interlinked. So I'm going to go ahead and write this equation, and that's going to be equal to 0 is equal to K1 x1 minus x2. And I'm going to go ahead and say minus x01 because that's the original spring length. So this is the new spring length minus the old spring length, and that's equal to the amount of stretch. And then plus FD1, which is C1 times x1 dot minus x2 dot plus M1 x double dot 1. Oh, dang. Whoops. This is the equation for FS2, and this is the equation for FD2. So, whoopsie, that's a 2, that's a 2. These are minus signs. And then we'll say plus K1 x1 plus C1 x dot 1. Okay, so that's our equation 1. And yes, these two are these two variables, these two are those two variables, and this one's here. And then we have our second constitutive equation. Both of these must be true simultaneously. And that is 0 is equal to Fs2. Well, Fs2 is this value, K2 times x1 minus x2 minus xo. I guess that's a 2, not a 1. Plus C2 x dot 1 minus x2 dot plus M2 x double dot 2 minus f of t. Well, this is super gross. How are we going to handle this? What are we going to do with these two constitutive equations? Well, we can rewrite this in matrix form, and it actually makes it a lot nicer. Okay? The idea behind this is that we're going to transfer this system into a bunch of single first order equations. Okay? First order means you have a derivative in terms of a non-derivative. That's it. Here we have double derivatives with x2, we have single derivatives, and we have non-derivatives. So a zeroth order, first order, and a second order. That makes it a second order equation. We're going to try breaking these, combining these, and putting it all into one single set of equations. So I'm going to go ahead and I'm going to define a y1 is equal to, let's see. We'll say y1 is equal to, hold on, let me look at my notes. I want to make sure I'm doing this right. I'd hate to tell it to you and then be wrong. Teacher's worst nightmare is being wrong. But we do it so well anyways. Oh well, whatever. Okay. All right, so we're going to say y1 is equal to x1, y2 is equal to x1 dot, which is equal to just the derivative, dx1 dt, and then y3 is equal to x1 double dot, which is equal to dx1 d squared x1 dt squared, which happens to also be equal to dy2 dt. And this happens to be equal to dy1 dt. So, fun fact, this column is interesting. I'm going to go ahead and say y4 is equal to x2. y5 is equal to x2 dot, which happens to also be equal to dx2 dt, which happens to also be equal to dy4 dt. And then we have y6, which is equal to x2 double dot, which the definition of that is d squared x2 dt squared, which also happens to be dy5 dt. This is the derivative of that. So that's fun. Now I'm going to go ahead and take all 6 of these variables and I'm going to replace them in these equations. And when I do that, you end up with 0 is equal to negative, so this is constitutive equation 1, negative k2 times, that is y1 minus y4 minus x02. x02 is a constant because that's the original spring length, minus c2, x1 dot is y2, x2 dot is y5, plus m1, x1 double dot is y3, plus k1, y1, plus c1, y2. Okay, now this equation doesn't have any derivatives in it. That's the kind of the purpose of this. Step 2, we got 0 is equal to k2, that equation, y1 minus y4 minus x02, plus c2, y2 minus y5, plus m2 times y6, because that's x2 double dot, minus f of t, and that's equal to 0. Now this is our 2 systems of equations. And we have the ability to take these and write them in a very different format. Okay? So with all of these equations, I have an equation for y2, y3, y6, y5, and y6 in terms of other y's. So what we have is y1 dot is equal to y2. y3 dot is equal to y2 dot is equal to y3. And then we have y4 dot is equal to y5. y5 dot is equal to y6. Okay? That's these 4 equations that we came up with where we have our equivalents. Sweet. And now we also have this giant thing, which we can solve for. We can solve for y5 dot because y5 dot is equal to y6 here. And we can solve for y2 dot because it's equal to y3. So if we were to solve these equations, we could plug them into this kind of a structure and get a matrix. I'm going to have to upload a separate video in a bit to finish this concept because I'm ran out of time. But you'll be hearing from me again soon. And we'll talk about how all